So I welcome you all to this second talk as a part of Swastibhavatu seminar series. Swastibhavatu, this distinguished sustainability lecture series, is established by Rawat Family Trust. Mr. Shishupal Rawat is our own alum from Electrical Engineering Department, and he was magnanimous enough to establish this endowment to invite people as eminent as Professor V. Ramaswamy, who is amongst us today from Princeton University. Earlier, the first talk was given by Professor T. Pradeep, who is another eminent water scientist currently based at IIT Madras. So we are honored to have you, Ram, today here, giving the second only in this series. So, of course, Ram don't need any introduction in the global climate scientific community, but nevertheless, I need to do this bit here. So, Venkatachalam Ramaswamy is Director of National Oceanographic and Atmospheric Administration's Geophysical Fluid Dynamic Laboratory. So, those who don't know this laboratory is credited to start numerical weather forecasting in the world. Am I right? And he's a professor in the Atmospheric and Oceanic Sciences program at Princeton University. Professor Ram has recently joined as distinguished visiting faculty at Kotak School of Sustainability at IIT Kanpur. Ram holds a PhD in atmospheric sciences from the State University of New York at Albany and was a fellow in the Advanced Study Program at National Center for Atmospheric Research, Boulder. His principal research interests are understanding the Earth system from weather to climate timescales using numerical models and observations. Ram has served on the Intergovernmental Panel on Climate Change, Scientific Assessment and Joint Scientific Committee of the World Climate Research Program. He's an author or co-author of over 200 peer-reviewed publications. He was a co-chair on National Research Council Decadal Survey for Earth Sciences and co-author of the International Committee on Space Research Roadmap, Observation and Integrated Earth System Science. He's also on the World Meteorological Organization Executive Council for Polar and High Mountain Observations, Research and Services. Ram is a member of US National Academy of Sciences, which is very, very highly coveted recognition, and a fellow of the American Meteorological Society, American Geophysical Union, American Association for the Advancement of Science, and American Physical Society. He is a recipient of the American Meteorological Society Houghton and Rosby Medal, American Geophysical Union Charney Lectureship, Distinguished US Presidential Rank Award, and the only 3-time WMO Norbert Gerber International Awardee. He was a member of the Intergovernmental Panel on Climate Change team that was co-recipient of the 2007 Nobel Peace Prize. Ram, all yours.
Okay, good afternoon and greetings, everyone. I'm really very grateful to Professor Sachi Tripathi for giving me this honor of delivering this Swastibhavatu lecture. I'm also grateful to IIT Kanpur for giving me this opportunity to speak to you all. This is my, I think, third or fourth visit to IIT. It's always been a distinct pleasure to come here and speak to colleagues and students and faculty members. Okay, really honored for me to be here, and also I've already met a lot of the faculty associated with the Cortex School of Sustainability, who, by the way, are also, I thank for inviting me here. I've already gleaned a lot of points about the School of Sustainability, very interesting for me to learn about them. And finally, in terms of thanks to the Rawat Trust for recognizing the importance of sustainability and endowing this lectureship. Really, it takes a lot of such gestures to really promote a field and to make it work for the human society. So really congratulations to the Rawat Trust for this exciting venture that they've launched. So what I want to do today is talk to you all about climate extremes and climate change in extremes, but more from the point of view of understanding. I think that's one thing that is always necessary before we get to predictions and projections of climate in the future. I think most importantly for sustainability, this is very key because you want to know what is it that, what is a problem and what is it being created by, what does it look like, so that you are actually able to explain solutions which you are prescribing for sustainability. So here's an outline of my presentation. I'm going to talk a little bit about Earth system and climate science and modeling. Now, I want to use the climate and Earth system words rather interchangeably. Basically, Earth system is, of course, the whole Earth system, the physical, chemical, dynamical, biological Earth system. Climate has generally been reserved for things which exclude things like biogeochemistry, ecosystems, whereas Earth system includes everything. So basic climate plus biogeochemistry ecosystem. So I'll talk generally about Earth system, but really a lot of that talk is going to touch upon climate science and modeling. I'm going to mention what we are sort of seeing as the energy imbalance in the Earth system, which is kind of now becoming very discernible from observations. And then the energy and water are linked. Basically, there's interdependence of that. And that nexus, I'm going to look at it closely in terms of what greenhouse gases are doing versus what aerosols are doing. And which leads to the next topic, which is the changes in the hydrologic cycle and precipitation in the 21st century. What do we expect? And then finally, I'm going to launch into a perspective on weather extremes in climate, which is kind of the thing that society really wants to know about. And I'm going to make use of models and observations as I go along. So let me begin with a little bit of a history of how GFDL came to being. So back in 1955, at that time, the first 24 to 48-hour weather forecasts were getting solved in the sense they've been predicted. So the equations were there, the equations are always there. The equations were formulated, even 50 years before that. But the actual translation of those equations into forecasts began only in 1954, and the first 24-hour, 48-hour forecasts appeared in 1950s in the public. Of course, in World War II, they did use meteorological forecasts, but those are all done under classified regimes. First public forecast was 1950s. And then so when that came into being, John von Neumann, famous eminent mathematician, who was at the Institute for Advanced Study in Princeton, really a true visionary. And he loved solving things on the numerical machines, the computers. So he asked that, okay, so you've done the 24-hour, 48-hour weather. How about looking beyond that? What does it look like beyond that? So he was not thinking of climate change or anything. He was just thinking of what does the weather look like? If you integrate the equations beyond 24 hours and 48 hours. So he called it, what is the ordinary general circulation of the atmosphere? Because he thought somewhere the atmosphere should become quasi-stable. So he was wondering when that happens, how does that look like? And so he said then the Joint Numerical Weather Prediction Unit, which was a forerunner of the Weather Service in the US, he said, asked them to set up a project to investigate the so-called infinite forecast. That's what he called it, to solve the general circulation problem. And he then suggested that the person, the lower right-hand side, the picture you see Joe Smagorinsky, he recommended that Joe Smagorinsky lead the formation of a research unit within the Weather Service to look into the integration of equations beyond 48 hours. So that came to form what is now called the Geophysical Fluid Dynamics Laboratory, but then back then it was known as General Circulation Laboratory. It was based actually in DC in a basement office just opposite the White House on Pennsylvania Avenue. And then in 1967, actually it began in 1966, Smagorinsky felt that he needed an association with an academic institution and not be permanently in sort of a government agency alone. So he then struck up this conversation with Princeton University, and in 1968, GFDL moved to Princeton, and that's where we are since that time. All right, so that's a bit of history. Let me now jump into the sort of core topic for today. So Earth's energy imbalance. So over the past 20 years, we've had continuous observations from satellites of the Earth's energy, that coming in, that going out. So if things were stable, you would expect that be zero, net gain and net should equal net loss. So only over the past 20 years have we had this capability. Whereas the technology for this existed back in 1960s. Back in 1968, the first satellite actually flew over the Earth, and it actually measured the net incoming and net outgoing energy. But then after that, interest was lost in that, and so it didn't pick up till 40 years later. All right, so here's the story of the energy imbalance. So, don't worry too much about the numbers, but there's 340 watts per square meter. It's a sort of a unit of energy per unit area per unit time. 340 watts per square meter comes in, 100 of those goes out. So the net coming into the system and absorbed by the system, the atmosphere and surface is about 240. But the outgoing is 239, which is in the form of infrared radiation. You'll notice there's a difference of 1 watt per square meter. That is the imbalance in the top of the atmosphere. Now, this has been measured by satellites now for 20 years, so we know what we are talking about. And what we're talking about is this. This is the result you get from the NASA satellite called Ceres. And just look at the straight line here. What you have here is a gain by the Earth of about 0.6 watts per square meter per decade. So over 2 decades, it's about 1 watt per square meter. That's considerable, because if you have 340 watts from the sun coming in, or 240 watts net coming in, out of that you're kind of not able to account for 1 watt per square meter. That is a pretty big deal. And this is now a robust observational trend. Okay, so now let's talk about the Earth system. So that was a problem. So now let's maybe see what we can do about it. So here is the Earth system as we know it today. Consists of the atmosphere, oceans, land, ice, and ecosystems. And basically ecosystems includes biology, both over land and oceans. And you see a schematic of everything that you probably are very familiar with. There is human contributions. There's atmospheric interaction between the oceans and the atmosphere. With the oceans, evaporation and precipitation, all the atmospheric composition, changes in atmospheric composition, atmospheric biosphere interaction on the far right. And so this is kind of picture we have. And what we seek to do is to represent it numerically or mathematically. And so in doing so, one has to understand that you have to obey all the laws that's given. So all the conservation laws have to be obeyed, especially for things like water. And there has to be continuity across the interfaces: atmosphere, land, atmosphere, ocean, ocean, land, and land ice and ocean ice. And basically, you recognize all these fundamental equations: thermodynamical equation, the equation of motion, radiation transfer, equation for water vapor, heat balance, and hydrology at the Earth's surface. So this is something which you have to obey, and so this is something that has to be done rigorously. Now, in terms of the ocean, there are other things which are also got to be accounted for. One is the transfer of momentum, heat, and then water. And then, of course, water in the form of ice and evaporation and precipitation, and then advection in the ocean to represent the characteristics of the ocean. So basically, these schematics are followed up by mathematical equations, And that's how we go about doing the research on these subjects. Okay, on to modeling itself. So obviously, you represent this whole system at every grid point on Earth, horizontally and vertically. And at every grid point, of course, you may have some ocean or no ocean. You can have only land, or you can have a mixture of land, ocean, and sea ice. And this is now how the picture is translated onto the computational grid. And then this is kind of the equations you see that are used on the left-hand side, and then the computations are performed in NOAA's R&D HPC, high performance computing, which is located in Tennessee. All right, so before I kind of launch into what some of the results of the simulations are, let me ponder a bit briefly about the processes in the Earth system. And this is where complexity enters in, and this is also the basis for uncertainties in what we do know and what we do not know. And there are some things we know we do not know, and there are some things we don't know that we do not know. Both are sort of incorporated in the slide that you'll see. So first of all, take the atmosphere. So what you see here is something represented on a 50 to 100 kilometer scale. So very, very small spatial scale. But within that, you can have all these processes happening. You have convection, building up clouds. You have interactions with the atmosphere. You have interactions with the radiation. You can have ice formation as you go to higher altitudes. You have aerosol particles, which also mix with the atmosphere. You have new particle production. And then you have all the associated dynamics with convection, including downdrafts. And then on the very smaller scale, you have things like scavenging by droplets, coalescence in droplets. It is impossible to represent all these on very fine scales, because then you need to go to micrometer scales. And micrometer is 10 to the minus 6 meters. Typical large scale motions that we worry about, like monsoon dynamics, are on the order of thousands of kilometers, let's say 1,000 kilometers. So you have to cover 9 orders of magnitude in spatial scale. Impossible to do it on present day computers. And you don't want to really do it that brute force, because you have to get at the understanding part. And if you spend all your time trying to just do this brute force mathematics, then it might take quite a few tens of years to understand the process. So we don't do that. But then that builds up the uncertainties, because you don't capture all these finer details. And I'll sort of reveal later on where this plays a role. Then there's the ocean. So ocean is not quiescent. It has no moist convection, so that's a relief. You don't have to deal with that uncertainty in the ocean like you do with the atmosphere. But it's got other things. It's got transports. It's got interaction with the atmosphere in terms of precipitation falling and then sensible heat transfer. It's got evaporation. It's got bubble breaking, sea spray out in the atmosphere. It's got transports in all levels in the ocean. And then, of course, you have topography in the ocean, so that interaction with topography actually creates its own dynamics. And all this happens in the ocean, which you have to also take care of. And the thing about the ocean that we don't really know very well there are two things. One is the mesoscale eddies, that is the eddies which form at very small spatial scales. And the other thing you don't know is about the ice sheets, which are, sort of ice sheets melt, they add to the fresh water in the ocean. And then you have land. Land is emerging as now a complex feature which you have to represent very carefully. And one of the things is the heterogeneity that prevails in soil moisture, evaporation, runoff, and then vegetation amount, which comes under leaf area index. And all these, this is a map of the US, but you see sort of the variation across the whole land. And this is just over the US. If you take other areas of the world, like South America or India or Australia, then the terrain is quite different. And so we actually use the GIS data, environmental data, to do the capturing of the heterogeneity over land. And it's not just heterogeneity, you also have slopes, hill slopes, which is very important when you're determining something like flooding. Because when you have slopes, flooding is going to be different than if it's a flat terrain. So now notice that all this is on very fine scale, spatial scale, but we do still run a coarse resolution over continental US or CONUS. But we do take the information from different regions, and this is over US, but also over the rest of the world, to actually incorporate the fine scale local information as best as we can. But there are still uncertainties coming up in the land. All right, so that's in a nutshell some of the complexities that we associate with the land, atmosphere, ocean, and land. So now let's go back to the problem of the energy imbalance and talk about the forcing of the Earth's system. So what are the forcers? So there are first of all natural factors of influencing climate. So you can have changes in the sun, which has been determined to be very small, but nevertheless there are changes in the sun. Over millions of years, this is going to be very significant. Then there is volcanic eruptions, which throw out sulfur gases, which then oxidize to form sulfate aerosols, and those particles reflect radiation. Once they sit up in the stratosphere, they are there for about 1 to 2 years, and over that time period, they perturb the Earth's energy balance. And then there is internal variability itself, El Nino, La Nina oscillations, where the internal variability also can be a driver of the system, because the internal variability can have time scales of 2 years, 10 years, 100 years. There are oscillations known, which have a period of 10 years. So all these can perturb the climate and can be responsible for driving the energy imbalance. And then, of course, we know these constituents, CO2, nitrous oxide, methane, and the CFCs, they all have been rising in the 20th century. CFCs are showing a decrease because of all the protocols that exist. But nevertheless, these are all greenhouse gases which are then strongly perturbing the climate. And then there are particulates, aerosols. And aerosols come in multiple varieties, multiple types, multiple sizes, which makes for the complexity and the uncertainty. So you can have aerosols which are entirely anthropogenic from ships. This is smokestacks. These are tailpipes of cars, diesel trucks, aviation. And then there are aerosols which are completely natural. This is due to DMS from the oceans. Then you have the terpenes from trees, which leads to aerosols. And then you have the natural forcers, volcanic eruptions, sea spray, which releases sea salt particles, sodium chloride, as well as some sulfate. And then you have a couple of factors which emit aerosols that can be from both natural and anthropogenic sources. One is dust, so it can be just desert dust being wafted into the atmosphere, and another is deforestation and urban buildup, which also releases dust into the atmosphere. And then forest fires, which can be, of course, natural or anthropogenic. And then the center is a satellite observation showing kind of where you see the aerosols in different parts of the world. They are not homogeneous, which is kind of a problem in tackling it, because unlike greenhouse gases, which are homogeneously, more or less homogeneous across the whole world, because they are long-lived gases, therefore live longer in the atmosphere, therefore they spread all over the globe. Aerosols do not carry over long distances because they get washed out or drop out of the atmosphere. And so they are not homogeneously around the globe. They are, in fact, at a peak when you are near urban areas. In fact, there's, just I captured this picture because it's a raw model, but it actually reflects something that's seen in satellite also, where dust is mixed with clouds that form essentially vortices that essentially form hurricanes. So you have this complexity of treating the dust and the water in the form of clouds together. And this is sort of one aspect of the complexity that we encounter with both aerosols and clouds. All right, so this is from IPCC 2021. The AR6 report shows the forcing that we know has happened from 1750 to this is up to 2019. So basically, it's pre-industrial to present. And then the horizontal bars you see are the uncertainty limits. So you see the very first one, CO2, is among all these things, it's the strongest forcer, but it has a very narrow uncertainty. So you're pretty confident about the forcing from CO2. Methane, N2O, all halogens, also on low uncertainty limit, we also are pretty confident about their forcing. Ozone, slightly more uncertain and also a smaller magnitude. Stratospheric water vapor resulting from methane oxidation, very small amount. And then you have the albedo change and the land use change, which is because of deforestation in the northern hemisphere. It's a negative forcing because you are changing basically the reflecting properties of land from very strongly absorbing to highly reflecting, which means it's negative. I forgot to mention, the zero line is where it's kind of if a forcing was 0, then it would cause no effect on the climate. If it was positive, then it's going to tend to warm the climate. If it's less than 0, it will be cooling the climate. And so land use, there is some light absorbing particle on snow and ice which cause absorption. But the big thing which actually acts opposite to the greenhouse gases is the aerosols. And there are two effects. One is the direct aerosol effect, that is, they just scatter radiation, and that's negative because it's a loss of radiation to the system. And then there's an aerosol cloud interaction, which is when the aerosol particles interact with clouds and make the clouds brighter. So when the clouds get brighter, that means you're causing a more negative effect, and that's why it results in cooling. So basically, this bar is basically trying to compensate for the sum of these bars. So total anthropogenic forcing, this is the human-induced forcing, is this much, basically coming from these areas. But the uncertainty is greater than you see for the greenhouse gases because of the uncertainty that results from the aerosols. So that's kind of an important point to remember as you go along, this uncertainty being an important one. And solar, is also here, but it's a very small magnitude. All right, so trying to understand the climate change. So this is again from IPCC. So one of the things that has happened, and this is a plot on the left, is showing the years from year 1 to year 2020. And what you see is the last 200 years is the observed record of temperature change. So you see it sharply rising. And before that, you see what is a reconstructed record, the best reconstruction that's possible from various data sets like ice cores and sediments. And what you see is that this has been the warmest multi-century period in more than 100,000 years. That is, over a 100-year period, this is the warmest that's been there in the last 200 years. And then if you look at the right-hand side is the result of simulations, several simulations. These are not just one model simulations. These are about 20 different models around the world simulated this. So if you had just the forcing from natural forcers, then what you would get is this almost a flat line. And the shading you see is the envelope from different models. So what you see in the solid line is the ensemble mean of all the models. So basically, that would not explain this black line, which is the observed surface temperature change over the last 200 years, and that's the global change. But if you add now the natural and human influenced forcings based on the diagram I showed you in the previous slide, then you actually match the observed changes quite well. Not exactly, but actually quite well, which is what leads to all the conclusions that IPCC has been making about the fact that warming is incontrovertible and that the warming is attributable in the major part to human-influenced emissions of greenhouse gases and aerosols. And it's not just surface temperature. Everything points to a warming world, temperature of the lower atmosphere, sea surface temperatures here, and then air temperature over the ocean. So this is a surface air temperature. And associated with that are increases in humidity. This is our surface level humidity. And then decreases in all the ice related areas, Arctic sea ice, snow around the world, as well as glaciers. And the global sea level is increasing, as well as ocean heat content is increasing, all pointing to multiple lines of evidence for a warming world. I have to go back to this, I have to go to this slide for a reason. This is actually, we have to ask, how good are predictions compared to observed changes? Here's an example of how the predictions actually have matched the observed changes. This is actually a plot, the bottom is a plot of observations, as you can see, from an average of 20 years in the present to 20 years back in 1960s, and basically shows the red and brown are showing a warming world. Well, the yellow is also a warming world. Yellow to red is all a warming world. Blues are where it's cooled. So these are observations. This is actually a model simulation done in 1989 by a paper by Stauffer Manabe from GFDL. And here is Suki Manabe, who just in 2021 got the Nobel Prize in physics for his work that kind of resulted in this plot. And that's kind of first climate Nobel Prize that anyone has received. He received along with Klaus Hasselmann from Max Planck Institute in Germany. But you see, this was a coarse model. This model had a resolution of 10 degrees by 10 degrees. You wouldn't dare do that in this day. Your paper will be rejected outright. But if you look at this, the three things that matter in a warmed world are these. And I can look at the observation. The land warms faster than the oceans in an annual mean, number one. Number two, polar regions such as the Arctic, not the Antarctic, but the Arctic, warms more than the lower latitudes, number two. Number three, northern hemisphere warms more than southern hemisphere. Those are 3 points that Suki Manavi made in this paper in 1989, and sure enough, the observations reflect that. Quantitatively, there are differences, of course, but qualitatively, that's kind of something that's borne out. And Manavi actually explained it through dynamics as to why you would actually expect these things to happen in a warming world. But this is a proof of, you always should ask for proof of, how good is your theory, how good is your modeling. This is one example of how things have come through. Okay, now I'm going to dive into a particular aspect of changes with the focus on the global hydrology cycle. And it's like a tale of two cities, but here it's a tale of two significant forcing agents, greenhouse gases and aerosols. So I go back to the energy balance diagram again, but now I'm going to focus on the surface. So at the surface receives, again, global annual mean, 160 watts per square meter in the short wave. That's the short wave radiation from the sun coming down to the earth. The long wave, so the surface has to emit back some radiation. The surface loses 56 watts per square meter due to the long wave radiation, infrared radiation. So what's left? Left is 103 watts per square meter, and the surface, to be in balance, has to exchange that with the atmosphere. So it sends back 103 watts per square meter through sensible heat and latent heat. Sensible heat is just the difference in the air temperature, roughly speaking, between the surface and the air above it. Latent heat is that through the evaporation from the surface, which then, of course, condenses in the atmosphere and comes on as precipitation. And the ratio of latent heat to sensible heat is approximately 4. So the latent heat is a much more efficient form of the surface releasing the energy than sensible heat. Okay, so now bear that in mind, surface energy balance. So first, before going to surface energy balance, I'm going to show a result from use the GFDL model. One of the things with modeling is that it's like a lab. And, climate of the planets is not something that you can do in a lab experiment. Like you can't create two Earths in the lab and say, okay, in one I'll inject CO2 so that I can find what the effect of CO2 is. You just can't do that. That's why you go to a computational model, because on the computer you can actually tackle this problem. So then you can also tackle another issue here, which is you can ask the question, what if the system were forced only by one forcing agent, keeping all other forcing agents the same? Or you take agent number 2. What does the system do to with agent number 2? So that's what these simulations represent. So this is actually a global surface temperature, and this is actually from the GFDL model. And the black line you see is the observation. So that's kind of what you have to match. The magenta line is what you would get from just forcing by greenhouse gases only. So you see that, after about 1960s, it just shoots upward. It doesn't match the observed curve. Then you can then ask, what about tropospheric aerosols, human influence aerosols? And that, of course, is negative because, remember, they were cooling the system. So they cool the system. And then there are some other forces like land use change because of deforestation, and that's a yellow line. And then the blue line is this blue line is the result of all the forcings. So notice, it doesn't match the observations either, but it does a much more effective job than any of the other curves in matching the sort of rate of increase, especially since 1960s, in the increase in surface temperature. So, and if you see kind of more of the particulars here, in this particular model, the greenhouse gas change over this period is 1.5 Kelvin. Aerosol cooled by about 0.5 Kelvin. So the aerosols offset the greenhouse gas effects by roughly a third. That's in the temperature. Let's look at precipitation. So in the precipitation case, again, Now, the precipitation observations are not as good as the temperature observations, partly because precipitation is a very inhomogeneous, transient field, very noisy. And so the best reconstruction of observations is black line over the last 50 years. Again, if you take just the greenhouse gases only, you're nowhere close to the observed precipitation. Neither is the tropospheric aerosol only, but they too are very strong, strong divergent from each other. And then if you look at all the forcings together, that's a blue line here, it actually comes close in terms of the order that you want to represent. Not satisfactory, but nevertheless, the thing that's interesting is in both the observations and in the blue line, which is the result of all the forcings, you see sort of a decrease. And then the observations seem to suggest an increase from about 1990s onwards. So does the blue line. And in the case of at least this model, the change due to greenhouse gases is 2 watts per square meter expressed in terms of watts per square meter now. Aerosol is minus 1.8. So one of the things to bear in mind from these two numbers is the fact that the aerosols have really dominated in terms of offsetting the greenhouse gas effects on precipitation, much more than they have on the temperature effects. And I'll come to the why a little bit later. So if you now the same result, if you look at it in a different fashion, this is the precipitation change with greenhouse gases only, so it's all positive because greenhouse gases actually tend to induce more evaporation and therefore more precipitation on a global scale over all regions. This is global, Asia, Europe, and North America. Aerosols do the exactly opposite because they reduce the sunlight at the surface, which reduces evaporation. When you reduce evaporation, you have to reduce precipitation for balance. And so this is all a deficit in precipitation. So notice that these two go in opposite directions. So the net result, with the exception of Asia and maybe a little bit of North America, is actually almost zero change in precipitation, no change in precipitation. Although this is over the 100-year period. And so only over Asia, you get some larger effect of reduction in precipitation only because aerosol content has been higher over Asia than really anywhere else in the world. Now, one of the things that aerosols do is most of them are in the northern hemisphere, very few in the southern hemisphere. So there's actually a dynamical mechanism which induces a shift of the intertropical convergence zone because the precipitation wants to move to a hemisphere which is warmer than the hemisphere which is colder. The northern hemisphere is colder because of the fact that you have less latent heat released in the northern hemisphere because you have less evaporation. And therefore, that drives circulation, which basically is a reduction of the Hadley circulation. And you actually see something in observed trends where you see the shift in South Asian rainfall over the period from 1950 to 2000, a weakening of the Indian monsoon, and the Saharan drought. You see all the precipitation belts kind of shifting southward, namely there's desiccation north of the equator, and there is almost north of the equator, and then there's sort of increase in precipitation in the southern part of the tropics. Some of this is actually seen in more recent observed trends from the IPCC AR6. The black lines, both the solid and dotted, are the observations, and you see sort of a sharp reduction in precip over to the 1990s, and then sort of an increase as you go further into the future. The ensemble of models are not able to explain all of this, but you do see the general decrease in the red line of the models, and then sort of a consequent increase. So qualitatively similar to when the inflection point is where the precipitation starts to increase. This is an important aspect, and again, I'll come to Asia because Asia had the largest decrease in precipitation, and therefore, by the same token, by the same argument, it has to have a more increase as we go into the future. And that's what this diagram shows. Again, if you look at different forcing agents, if the system were forced only by greenhouse gases, you'd get the green line, which is basically almost a monotonic increase in precipitation from 1850 going over 2100. And we are here, of course, in the present. If you had aerosols, one of the things about aerosols is that they tend to reduce the precipitation, which is the blue line here, but aerosols are going out of the atmosphere, partly due to cleansing by countries, which are stopping the pollutants from entering the atmosphere, and partly by cleaner technologies, which are actually pumping less aerosols into the atmosphere. But because of the removal of the aerosols now, look at the blue line. The blue line actually suggests now that about from 1990s, there would be an increase in global precipitation because like a thermostat effect, which has been removed. The aerosols were counteracting the greenhouse gases, and now you remove these aerosols and greenhouse gases go full tilt. And so the net result in the future of increase in greenhouse gases, and I'd say this is following the SSP 4.5 scenario, which is the middle of the road scenario, increase in greenhouse gases, decrease in global aerosols means that you follow the spring curve, which means a rapid increase in precipitation more than what we may have seen in the past 50 years. This is the global mean, so it doesn't mean that every region is going to see an increase, but this, in the global mean, this has to be true from just a theoretical perspective, and it's kind of borne out by simulations. Okay, some sort of changes over India from this model. So again, if you look at just the three panels, so this is from 1990s minus 1950s, so it's the last 50 years of the 20th century. Yellow is the warming, so you see the warming due to all the agents together. Greenhouse gases give you a larger warming than the net, and the aerosols are responsible for the decrease that you get between the greenhouse gas and the total forcing. So that's the past to present. If you look at the future, same scale, the scale hasn't changed. You see sort of the more of increase from the greenhouse gases. This is sort of related to 2000, so it's actually adding to the increase that you saw in the previous previous slide. A little bit of aerosol effect still remaining in terms of temperature, but generally a further increase when you sort of look at all the forces taken together. And then this is sort of looking at the future in terms of precipitation. Sorry, this is the past in terms of precipitation. You see the aerosol forcing actually has been responsible for reduction in precipitation, particularly in the northern part of the country. And this is what I mentioned earlier about the aerosol content, reducing the precipitation, driving it more southward. And greenhouse gases, of course, tend to mostly increase through evaporation, more evaporation, and that's kind of reflected in this panel here where you see an increase. And then just sort of following up on the earlier argument for the global mean, for the future, you see, something here. So in the future, the reds mean increase in precipitation. So greenhouse gas on the upper right panel shows an increase. And now the aerosol panel shows also an increase, particularly over the Indian continental region, which then together adds to more of an increase over Asia. So over the Indian subcontinent, at least the global measure that we showed in the earlier plot is actually followed, namely the decrease in aerosol is actually leading to an increase in the precipitation over India. All right, so one of the things that arises is, these were like projections following some scenarios. One of the things about the projections is that most of these were looking out to 2100. Increasingly, the question being asked is, what about the next few decades? As we go up to 2100, what does that trajectory look like? So we start exploring something where we are actually engaged in prediction and projections of changes in the Earth system. And one of the first things that I want to point out is the potential for landslides before even the end of the century. And these red dots that you see are glacial lake locations, mostly in Nepal. And the gray and the black contours are the percent change in potential landslide activity going up to anywhere from 40 to 70%. Basically, as you warm the Earth and you have precipitation falling, warm precipitation falling, you can actually break these glacial dams and then release a torrent of water, causing mudslides and landslides. This is not so far something that is happening on a colossal scale, although there are cases, I think even in the Uttarakhand case, where there's a Uttaranchal, I guess, case that is one plausible factor in terms of the massive release of the water. But this is something that is, again, a consequence of just the increasing warming of the globe, that the rate of increase in landslide by the end of the century is expected to be greatest over what are current glaciers and glacial lakes. Then, we have this very interesting issue that we have increase of tropical storms over Arabian Sea in the recent decade. I am sorry, you can't see this very clearly, but this is like sort of what the projection of tropical storms is, the October-December time period over Arabian Sea in the present. This is what it looked like in the 1940s. So lesser, you can see that less storms between 40 to 2000. But this is going into the future, and this is actually going out to 2015. But increasingly, what we see is that the tendency for Arabian Sea storms to be there in contrast to previous decades. We don't fully understand this. Part of this, there's a reasoning that this is due to the aerosol content essentially going down over Arabian Sea. But there's probably more factors involved, but it's something that is still a puzzle as to capture it properly in these models. And then closer to the US is the predictability of the frequency of summer hot days over North America. Now, you would think that external climate change should be sort of the major reason for this, and it is a major factor, but there are two other components which are involved in the predictability. So this is different from projections. And one of them is just the North Atlantic and the North Pacific temperatures, and so the difference between them, as well as the soil moisture over the US. It brings into sort of the fact that the complexity in predictions is, it will go beyond just the external forcings and involve these interannual variability factors. And then there's ENSO, Central Pacific El Nino, has this dipole moment, as this dipole contribution to frequency of hot summer days, which is also important in determining the predictability. So this, as you go into predictions, you start to get into more of the flavors of what is involved beyond just the external forcing agents. This is regional sea level changes, and this is actually from IPCC AR5. One of the things it shows is how sea level rise is different in different locations. So global sea level is rising, no doubt, but regional sea level is different in different places. So in places like, for example, San Francisco, Charlottetown, it's increasing because of the warming and therefore increase in the volume of water. But there are some places where in Stockholm, it's actually not increasing at all. In fact, maybe you can even suggest it's decreasing. That's because the land is rebounding from the last ice age. So even though water may be rising, the land is also rising. So that competition makes the sea level rise at Stockholm a combination of a geological factor as well as a climate factor. And then a place like Manila, it's dramatic, the increase, as well as if you look at the coastlines of Bangladesh. And then Pago, which lies in the Central Pacific, you have the ENSO phenomena where there's a lot of variability from year to year, so there's no clear trend. And then if you look at the IPCC scenarios and what they give about, up to about a 0.75 meters of rise, but evolving slowly, so almost monotonic, the global sea level rise. But this is only from the expansion of water. There's a contribution that may be coming from especially the melting of the ice sheets, particularly the Antarctic ice sheet. And then if there's ice sheet instability, then it has the potential to go well beyond 1 meter. And then finally, the September Arctic sea ice, this is where we are. Sorry, actually being somewhere here. And indeed, Arctic sea ice is retreating, especially summertime sea ice is retreating more and more year by year, but there's a lot of variability. The trend is one of decrease, but there's a lot of variability. As you can see, sort of as captured by the models, the variability is very large. Some models make the ice completely disappear by 2060, and some actually do not at all to 2100. And this is sort of an uncertainty that comes because of the uncertainty in the cryosphere physics. Oh, and lastly, because of sea level rise, is another thing which happens, which is the increase in storm surge. Increase in storm surge happening because of the increase of water vapor in the atmosphere, increase in latent heat, and therefore there's more storms. But now the storm surge on top of sea level rise, can be appreciated on these two curves. Blue curve is like a control simulation where nothing is changing. The red line is where the CO2 is increasing 1% per year, which is about the rate at which it's increasing. But then, of course, there are excursions from both blue and red lines, even from the blue line, even in the normal times, because sea levels sea level can rise up without even any without any forcing. But then, as the red line, sort of you see it increases, so the spikes that are going up in the red part of the story are more. And so if you just see a statistic on 1 in 10 years, these kind of surges happening 1 in 10 years, and by the way, this is for New Orleans, which is of course very, very much prone to these kind of rises. You see the red spikes more often than the blue spikes, means that the probability of these spikes occurring in a warmed world much more than in a world otherwise. So this is something that is part of the story of predictions, going beyond just the projections. And finally, this is something I didn't talk about biogeochemistry at all, but one of the things that we can do now with predictions of the Earth system is the climate predictions actually resulting in prediction of chlorophyll. Basically, chlorophyll forms where it's upwelling in the oceans, bringing the nutrients from the bottom of the ocean to the surface. And all these red areas that you see are where the chlorophyll prediction skill can have a lead time of 1 to 3 months, which is saying something that you can actually predict some of the biogeochemistry occurring in the oceans by virtue of good climate predictions. And then, there are these various places in the globe. Everywhere is actually a very encouraging sign of what predictions you can make. All right, so my final part of my talk here is all this means very well for science, but how can we sort of do something which is getting to be more pertinent and relevant information for society besides communicating the science? So one thing to remember is that increasingly now, every area that you can think of, every sector you can think of, is demanding information from climate. It's not even a request, it's actually a demand. They want to know exactly when the next hurricane is going to come, which of course you can't tell, but this is the state of affairs, that you want to be ready to respond with a communication about that. And, all the sectors are listed here, I don't have to go over them. And because economies depend on that, livelihoods depend on that, and quality of life depends on that. And these are not cliches, these are becoming realities, really. And, one of the things that a lot of the people who work on social policy think of this as really a sort of a juxtaposition of 3 things. So weather and climate events, obviously, that's kind of what we've been talking about so far, but then exposure and vulnerability also being important. Exposure being in the wrong place at the wrong time, and vulnerability is predisposition of a group or a country being adversely affected, and that gives rise to a risk factor. This is, of course, what everyone is after. Climate and weather events are giving one piece of that information. It's got to be juxtaposed with the other 2, and that's an entirely different lecture. But that's kind of where things are being sought after. Now, what we, I think, at GFT and Princeton are very much interested in is the seamless modeling of the weather and climate system. So weather and climate used to be treated as 2 different compartments, and there are 2 different models, 2 different sets of analysts, 2 different interpretations. We think that that's an outdated concept now. Weather to climate is seamless. There's no reason why what you are describing as part of weather cannot apply to climate. Okay, it's a longer time scale, but part of climate. You see some of these things listed here, they occur on monthly time scales, seasonal time scales, decadal time scales. We ought to know all of that. So you see a whole range of things. Plus, we ought to know the internal variability as well. So the internal variability so far, we have gathered, internal variability over like 100 years, 200 years, we don't have the record for that from observations. Assemble that from models. We run the models without any forcings, and then the variability you see there, we interpret that as the variability of Earth system. How good is it? That's kind of has to be forced open more by data. And so in 2012, the National Research Council of the Academy of Sciences recommended unified modeling approaches. Don't have two different models. Use the same model. And we're trying to do that. That's kind of where we kind of have our quest set on. And one of the things that now, IPCC reports apart, which I've been talking about all the global scale things, there's now a real thirst for what's occurring in the regional scale. And regional scale means getting into all these local phenomena, all the phenomena which tend to remain local, like heat extremes, wildfires, sea levels, monsoons, hurricanes, air pollution, ecosystems, coastal inundation, El Nino, hydrology. I mean, these are now, people are asking for information on local scale. So that's where we have to deliver with the best possible science. And so finally come on some of the things. I don't have time to elaborate on all of these, but one of the things we're doing as part of venturing into the AI introduction into the climate system is creating what is called the digital twin. Basically, we are doing digital twins all the time. Remember, all the models we talked about are all digital twins, really. But now it's escalating to a different level where you want to ingest really all of the Earth system observations to do the Earth system predictions. So with high resolution models. So this is kind of a high resolution model, 3-kilometer global scale, and then AI-based data simulations going into that to form assessments. So this is sort of one step, if you will, to engage in this transfer of science to societal relevance with some degree of rigor. And then now going to another example here, this is actually an application of a machine-learned venture where we partnered with the Allen Institute for Artificial Intelligence, AI2, and basically we took a 3-kilometer resolution model, which is the highest resolution model that we were able to run, and put the moist physics from that model into a 200-kilometer coarse resolution climate model. Basically, the question was this: 3-kilometer model with a fine resolution can simulate moist physics, convection, precipitation much better than a low resolution model. But we can't afford to run a climate model at 3 kilometers, don't have the computer resource for that. So instead, we asked the question, supposing we transfer the moist physics performed in this more exact model to a low resolution model, does it improve the seasonal precipitation? And what you see is, the result is here. The blue is the model baseline. The orange is the improvement in precipitation. So, or it's a reduction in bias. So you get about a 15% improvement, 15% improvement in all seasons versus without machine learning being applied. You'll say it's very modest. Yes, it is modest, but even 15% consistent increase over all seasons is an improvement with kind of the very first venture that we've done with AI ML application. Now, undoubtedly, there's going to be more exact ways to do this. And the other one is from oceans, where we are using a high-resolution ocean model to actually infer subsurface dynamics from climate model surface data. The theory here being that if you can assemble enough data from a high-resolution ocean model between what's happening in the surface versus subsurface, then to do predictions of subsurface, you don't have to resolve to high resolution necessarily. You can just apply, because it turns out that that there are this manifold learning to reduce huge dimension of full variable space to smaller space meant that we could deal with just 6 regimes in the ocean. And dealing with 6 regimes in the ocean, rather than the whole ocean, is a tremendous scale down. And so this is something that we've now started to use satellite data, which can get the surface properties to actually infer subsurface. The reason why subsurface is important is because when you want to talk about seasonal to decadal forecasts, what's happening in the subsurface ocean below the mixed layer becomes very important to do those predictions. And so instead of running a full ocean model, you can actually resort to this method. So I think this is a theory which looks like it may be working, but still it's kind of in the works. All right, I think this is my final slide. So this is kind of where we're going in terms of now that we know that climate is changing, we want to ask the question of, okay, next 3 to 4 decades, what's coming up? I think that's the important thing. We know what's going to happen in 2100 with the current scenarios. We pretty much know what's going to happen, but the key question is what's going to happen in the next 3, 4 decades such that, it may be not even my generation, maybe the next generation, but the next generation has a handle on it rather than 3, 4 generations from now. So can we do that? Frequency of occurrence, location, severity, duration, early alerts, so they can forecast a very intensive monsoon or intensive storm season well ahead of the season. And then multiple extremes. So one extreme leads to another, like wildfires lead to air quality issues, lack of precipitation leads to wildfires. Can we do that more than a season in advance? So that's kind of where the concept of weather extremes under climate changes is going. And with that, I thank you for your attention, and I have taken more time than I thought, and I really appreciate you all sitting here and listening to talk, and I'm happy to take any questions now. Thank you.
I have one query about by using this simulation and modeling, can we predict the different types of harmful elements dissolved in precipitation, and how these affects our biodiversity over the years on our Earth?
Sorry, I couldn't quite catch the question. Can you just ask the question again,
Sir,
please?
my question is, by using the modeling and simulation which you are using, can we predict the different types of harmful elements which are dissolved in precipitation?
Sorry, harmful what?
Harmful elements.
Events, harmful events. Can you predict?
Elements.
Yeah, so yeah, that's a good question. I'll just answer that before you go on to the second question. Yeah, that is what we want to do. But, even if we think of like a seasonal forecast, it is very difficult to predict exactly when some event, very catastrophic event is going to occur. What you can predict, in certain instances, not in every case of every event, certain instances you can actually predict a season in advance as to what the probability is that you're going to get more storms or less storms. Like for example, in the US for the Atlantic hurricanes, the National Weather Service actually predicts so Atlantic hurricane season is May to November. So they actually predict what is the probability of it being a very active season, but by very active, I think it's meant like 8 to 10 storms, or a moderately active season, which is maybe 5 to 8 storms, or a low active season, which is 2 to 3 storms. So they give that range. It's not quantitative, but it does point to whether if it's 8 to 10 storms, I mean, everyone better, take caution on that. So it's not where we want to be, but that is kind of how it's going to start out, where you give probability of things happening. In the case of, for example, Western US, especially over California, the prediction of atmospheric rivers, very intense precipitation events, it's now possible to do it about 8 months in advance. So if, typically this happens in March, April time period. So now actually you're able to predict from models in June and July as to whether it's going to be a very active atmospheric rivers season, heavy precipitation at all. So individual events, very difficult, especially beyond 24 hours, 48 hours, it's very difficult. But probabilities or declaring severities of the events over the course of a season, there are some possibilities emerging now. I'm sorry, and what is the second question?
The second is how these harmful elements affects our biodiversity.
Affect our?
Biodiversity.
Biodiversity.
Yes.
Not sure I can answer that fully. I know that, especially the last slide, I put up multiple extremes. So one of the things that we are studying is the effect of climate on seasonal and decadal scale, what it does to the marine ecosystem, like fish habitats. Because, for example, one thing that's happening right now is in the northwest Atlantic, which would be like Maine, Gulf of Maine. It is the most rapid, it's the most rapid warming, most rapidly warming than any other part of water anywhere in the world. It's a very shallow sort of stretch. The predictions for the next decade, admittedly, it's from our model, so you don't take it for granted. But the predictions are that the decadal changes are going to now go in the opposite direction, such that it's going to warm, not cool anymore, because of various things in the climate system. But what it means for fishermen is the fish are actually going to move. The fish don't like warm water. They like to go to colder waters, so they're going to move out of the area. So, in terms of harmful effects on biodiversity, I can give you an example, is that the fish, if they stay there, they'll die, they'll move out, which has an effect on the economy because, the fishermen now have to travel, instead of 10 miles out of the ocean, they have to go 100 miles, which means more fuel, more time, and, it's kind of a cascading effect on everything, including the economy. So that's one example. I know it's not a biodiversity example, strictly speaking, but there are effects, for example, from wildfires on vegetation. Basically, vegetation is lost, and because of that, species are endangered because the species no longer have a habitat that they can kind of live. So wildfires is another example of where biodiversity is affected. Thank you for your question.
Okay, thanks.
Yeah, thank you, Professor Ram. I think that was a really inspiring talk. My question is, so now climate models are becoming increasingly complex, and for good reasons, of course, but that comes at the cost of losing the interpretability. And I think time to time, the need for hierarchy of models have always been emphasized. Now my question is in context of Indian monsoon, because when we talk about Indian monsoon, models still struggle to reproduce rainfall. And then we use the same models to do the projections. Do you think, yet Indian monsoon is a very well constrained, because if you look at the interannual variability, it's not so much. Do you think going into a direction to have to develop a simple physical model for Indian monsoon is a good way to approach how the monsoon is going to change? Or do you think simply the process is so complex that developing a simple model around it is not a good idea?
Obviously, keeping things as simple as possible is very desirable. And simply building complexity for the sake of complexity is not a good idea. Yes, things sometimes are complicated, but it doesn't mean that you got to build necessarily the most complex system. What is important, whether it's simple or complex, is testing the models intensely. I think there's a tendency these days to rush into complex things without testing them properly, or testing them in a very limited sense. But that doesn't really address the whole issue, because if you don't test the models, let's say you have a model and you want to introduce a new formulation, new parameterization, you've got to really test out the whole model on the results of introducing the parameterization. If you don't, you're inviting some trouble later on, because what you may have introduced as, let's say, the correct parameterization for something, it may be the correct parameterization based on all known laws of the world. But if it sort of interacts poorly with the other components, you may have solved the problem of that physics component. Let's say aerosol. Suppose you have the best aerosol parameterization. You may have solved the aerosol issue, like predicting how much aerosol there's going to be on a given day, in a given month. But if it messes up the, shall we say, clouds, okay, then you've defeated the purpose. So there's no point in just building up complexity or sake of complexity. It is very important to test out the models at every stage. Because, and obviously it becomes difficult because as you add more and more parameters to your model, it means more difficult to test these things. And the guy I talked about, Suki Wanabe, the world's first coupled modeler, climate modeler, always had this paradigm that he wanted to keep his model as simple as possible so that he can get a lot of experiments done with the model. I mean, it seemed like a very simple thing, but back in his days, he emphasized. In fact, just to give a personal anecdote, I mean, when I came to GFTL, I wanted to introduce a parameterization for methane. Manabe was running his model with only CO2. I told Manabe, it's back in 1990s. I said, Suki, this methane is very important, And he said, yeah, I know it's important, but I'm not going to have it in my model. Why? Because it's going to take years for you to construct a proper model, which is stable under this new component. Then you'll spend some time trying to test it, and by that time, I'll retire. So I don't want to do it. But, I mean, he started jokingly, but I think the principle is important, that you have to understand what a model is doing in its wholesome thing, and not just the one component that you are wanting to test out. So, I mean, I don't know what the answer is. I mean, I think it is you build up the model's fidelity more than just the model's complexity.
So you had a slide on chlorophyll content, right? So is chlorophyll content increasing worldwide? What was it about?
No, well, no, that was just a prediction of the chlorophyll, due to the upwelling response to the warming.
Okay.
So it's kind of indirectly kind of just the response due to the increased upwelling.
I see. Okay. Thank you.
Hi, Professor. Nice talk. So do you want to comment something on these Uttakashi floods? And do you think that, is there any probability, or what is how can we say it with more certainty that such kind of events can happen in future in so and so regions so that the impact of these events can be avoided?
Yeah, I mean, I think isn't this the second event of its kind in 4 years or 5 years that it's this mudslide and landslides have happened in that part of India. I think it's first important to understand what happened. From what I've read so far, I think it's not clear exactly, was it a cloudburst only, or was it a cloudburst combined with some natural dam breaking apart because of just the volume of water coming through. So I think we have to understand that first before we start speculating on what exactly is the reason for that. It is, quite a lot of factors are plausible on this. I mean, the one factor which is common to all this is the heavy precipitation that did fall, which started all this thing. So to answer your question, I think we need to have some more work done in trying to extract what was the cause of the mudslide, because heavy precipitation, yes, but then what happened after that? Was it sort of lakes, the natural lakes that formed breaking off, or was it just vegetation not being there to arrest the slide of water? I haven't read it fully, so I'm not sure what the current consensus is on what happened.
Thank you, sir. It was a great presentation. Sir, my question is as you mentioned that what is going to be next 3-4 decades is much more important, right? Whether we're talking about century or that one. So, so is it because of these extreme event have this these kind of occurrence of these in the decadal level of that?
Sorry, can you hold the mic?
Okay, so what I'm asking is as you mentioned that what is more important is what is going to be next 3-4 decades, right? As you're talking about century. So is it because these extreme events occur in this time scale? That is number one. Second is like right now it is also much more important to talk about the seasonal forecast, because seasonal forecast like a lot of more application like give immediate solution in terms of a lot of applications are there. And adding the first question is when you talk about this 3-4 decades time horizon, is it also because of we can plan more better adaptation and resilience strategy? That's why we're talking about this 3-4 decades time horizon. Yeah, thank you.
I mean, yeah, a couple of things to note here. One is that what we are seeing is greenhouse gas is increasing. I mean, it's just a fact of life. It's increasing, and it is going to create more disequilibrium, the energy balance. Of course, just lack of equilibrium in energy balance doesn't mean that extremes follow. There's a correlation, but it's not necessarily a very high correlation that extremes will always happen when you increase energy imbalance. But what we are finding is that indeed that is so. And the question is, we know continued increase, in the forcing of the system, what it will do in 2100. But I think, the question increasingly is, what is the trajectory to 2100? Like, if you take, let's say, a number of extreme events, between now and 2100, what is going to be the trajectory of the number of extreme events happening? If you look back from 2000 to 2025, at least the perception of extreme events has increased. It may be that previously they were happening and we didn't notice them. Possible. But I think more likely explanation is that they have actually increased. So that perception is the reason why there's actually an urgency to know what's going to happen over the next 2 decades, 3 decades. Yes, 2100 is also important, but next 2-3 decades, come on. If you're saying that things are going more disequilibrated and more extreme events happening, why can't we try to answer the next 2-3 decades before we answer or while answering 2100? So I think there's an urgency there that is being called for now because of the evidence that is mounting. It's not even, you don't have to even delve into a lot of quantitative analysis. It is actually happening. And sorry, I forgot the second part of the question. Oh, seasonal forecast. I mean, I think seasonal forecast is going to be a very important regime that we have to do, because what happens is the daily weather forecast relies mostly on the atmosphere. So you take the conditions today, integrate the equations for one day, you have the 24-hour forecast. All it requires is good data observation, good observational data. You can actually forget all the physics. If you have good observational data, you can do the equations for tomorrow very well. And you can see it in a lot of, obviously there are some things you'll miss out, like extreme regional precipitation. Those things are maybe need some physics, but good observational data will get you 24 hours. Beyond that, the role of oceans comes in. And as you go to, especially decadal, the role of oceans becomes paramount. What is the ocean going to do? Its heat content going to do? Seasonal is where there is this transition where we feel that both this data initialization and predictions combined with the external forcing, which kind of manifests in the role of oceans, the two are together very important. You can't delete one or the other. Both are important. So that's why the seasonal is a very good test of how well we are actually understanding the science. So seasonal forecast, and also seasonal is something is realized very soon. You're doing it in 90 days.
I think we'll just take one question.
Yep, okay, sorry.
Thank you so much, sir, for such an insightful lecture. Sir, just one question. While explaining Earth's energy imbalance, you had mentioned about the role of oceans, and there was a point mentioned of transfer of momentum. I was quite intrigued. How is that linked with Earth's energy imbalance, sir?
Transfer of momentum. Guys, I don't think I said anything about transfer of momentum. What did it say? Remind me what I don't think there's any connection. You're right. It's not direct connection. I can't think of how energy imbalance necessarily leads to some defined transfer of momentum.
Okay, so Ram is going to be here for another 10 days. If you have some questions, you can
Yeah,
always reach
please.
out to him.
Yeah, or send me email. I'd be happy to answer them.
Because there is some other events. So we take Ram, a small token, and then.
Oh, very good. Thank you very much. Thanks, Chuck. Thanks.
Great.
Sorry, did I overshoot? Sorry, I overshoot.
No, I think it's all
Okay.
in time.
Oh, thank you so much. That's very nice. Thank you, sir. Yeah, thank you.